Thank you for having me, and thank you for putting on this conference. One quick word of warning before I start. Just moments ago, my internet cut out, but I was lucky to make it back. Should it happen again, I guess it's just one of the perks of living in Zoomlandia. I apologize in advance, but let's hope it doesn't. So I'm going to present on a little project that I've been working on with my student, Matt Scoggins, at Western Washington University. And the question ties in some of what we heard yesterday already about this quantization condition that, for example, pops up when you take this Nelsonian stochastic approach, but also in some other approaches. So let's start with some common ground. This audience in particular knows about pilot wave theory, so the introduction here will be very short. We know that pilot wave theory has this dual ontology. There's a wave function, and then there's this actual point in the configuration space that encapsulates what the actual world is like, right? So it kind of determines almost as if it were classical, except it's not guided by classical dynamics. And then the way this theory is usually presented is we imagine we have a large ensemble of those and maybe a large collection of hydrogen atoms. And for each one, we can look at it and we can place a little dot in our configuration space. And so we get a density. Now, it's so unclear how to interpret this notion of the density in cases when you have a system that doesn't come in an ensemble. Like you take the whole universe, you want to talk about the wave function of the whole universe, or like the quantum mechanics of the whole universe. Or it's just some complicated molecule, maybe some complicated DNA molecule that only exists once, right? So there's a question there. How do I interpret this notion of the density? And also, do I even need to? Right, that's another thing we can ask. But let's start with some reminders. If you just look at standard pilot wave theory, non-relativistic, let's keep it simple. You have the continuity equation for the density and also for psi squared, the mod of psi squared. You've got the Hamilton-Jacobi equation. Essentially, it's like the classical Jacobi equation, except with an additional quantum potential added to it. And I think everybody's familiar with those. And then the theorem goes that if initially the density is psi squared at one point in time, then that equality is going to hold at all later points in time, right? At least assuming that initially the momentum is equal to the gradient of S. There are a lot of subtleties in all of this, of course. And then the phase, this S that is the phase of the wave function, looks somewhat like, and we have to be really careful here about how we're saying this, but it looks somewhat like a sort of Hamilton principal function. Now, because of those equalities of rho equals psi squared, at least in the equilibrium pilot wave theory, and the fact that S sort of seems to have this classical this classical connotation, one can ask, can we eliminate the wave function altogether? Right? So can we sort of eliminate it and get out something else? Now, if we go through with that, the answer is yes, we can, right? So mathematically, all we do is we take the mod of psi and replace it with the density of, like the square root of the density. And then we have the velocity, essentially it's a velocity field on configuration space together with the density, and those allow us to reconstruct psi up to a global phase factor. And the global phase factor is not really physical. And if you're now worried about something like the PBR theorem and don't we need a wave function, well, all the information is still there. So something like the PBR theorem is not a problem for doing this.
There is a question. Sorry.
Oh yes, sorry, my apologies.
Lee Smolin, please.
Yes, to go back to your
Sure.
two extreme cases, when rho it refers to an ensemble, which is an actual big ensemble, like the states of a hydrogen atom in the actual universe, can we not make that the definition of it? And when there isn't a large ensemble, can we just say that quantum mechanics doesn't apply to systems that don't have many copies?
That is something we can say. I mean, I'll actually come to that as an option. So yeah, so density is clearly defined, right? If we have lots of copies of one thing, but if we don't, then one option is we sort of forget about it, right? But it's always an option. Let's not do that. One thing is we can say it must be an ensemble of something else. Like, I guess I'm going to jump ahead a bit. Some people will say sort of other parallel universes or something. So terminology is extremely problematic in all of those cases. Or you can say, like you're suggesting, no, there is no ensemble. Therefore, quantum mechanics doesn't apply in the usual way. That's totally.
But something
totally
else applies. Oh, sorry to interrupt. Something
No,
else
go ahead.
applies. We can work it out, and we get new predictions.
Right. Yeah, you will.
We get predictions that come in an order of 1 over the number of systems in the real ensemble.
I mean, you will get a different physics, right? If you
yes, but I can postulate that different physics and show that it goes to the, in the case of a large real ensemble, it goes to the Schrodinger equation. And in the case that there is no such ensemble, we get corrections to the Schrodinger equation.
All right, yeah. That is quite the possibility. And I mean, I think partly what you're referring to is one of those models that that you proposed with the maximal variety, and I'll refer to that too a little bit.
Yes, well, thank you for it's on the way to that. Yes.
Yeah, no, definitely. It's the concepts are are there for sure. Let's go back. Sorry, go ahead.
Yeah, then I wanted to ask one more question. What about the cases of ensembles? You talked about the wave function of the universe, or the wave function of a DNA, most of which may exist just once, but most DNA don't exist at all, which I think is even more interesting.
Sure. I mean, I think that takes us down sort of a different path that would create, I think, its own talk that we'd have to consider very, very carefully. So I think that discussion, I think we can have in a breakout room afterwards. But there's a lot to be said here, right? And I'm going to sort of glance over a lot of the conceptual subtleties that go into it, and in fact, a lot of subtleties that we or any practitioner of any aspect of pilot wave theory is going to glance over constantly, right? It really should be addressed and thought about much more carefully.
Great, thank you.
Sure. So let me carry on. So mathematically, this step is easy, right? Throwing out the wave function, replacing it with the square root of density, and having the velocity field, essentially the spatial gradient, and sort of reconstruct the phase that way. Conceptually, what we're doing is pretty radical, right? We're throwing out the wave function, and we're saying instead, those other systems in the ensemble, in the immediate neighborhood of the system that our actual world that corresponds to our actual world, those have a real physical influence, right? And so that leads us down to one of two options. Like I'm sort of saying here on that slide, either you're committing to the fact that those hydrogen atoms on Neptune, they're going to affect my hydrogen atoms in my lab. Or you have to say, well, those other systems in this configuration space, they are real things. Right? They are sort of real things that are not in our actual world, they're separate sort of universes. And if you want to apply that framework without modifications from quantum mechanics to the entire universe, you'd be forced in that kind of position. Now, any framework that throws out the wave function and just deals with density, I'm going to call a configuration space density framework just to have a term to be able to talk about it. Right? So this terminology is convenient right now for our immediate purposes. And there are a bunch of examples. And many of them are very similar. There are two that stick out. One is the Nelson stochastic mechanics. I included it here in part because it was featured a lot yesterday, and it does run into the same sort of conceptual issue that I'm going to come to in just a minute. The other one is actually kind of what we were just talking about, is Molin's principle of maximal variety, which if the conference program is to be believed, we're going to hear a lot more about later in this conference. And the reason it stands out is exactly because it is about systems in our actual world with a finite number of them that may approximate to quantum mechanics if the numbers are sufficiently large. The other ones, they differ in details in how they approach it, but in the end, again, I'm skipping over a lot of details here, but they end up kind of in the same place, maybe with different justifications, different underlying axioms. But for any of those, you're going to run into a certain issue, right? And that issue we've already heard about in the particular context of Nelson's stochastic mechanics, and that's the so-called Volstrom objection. Although the idea actually goes a little bit, the observation goes a little bit further back. And what Volstrom said is this, and he did it in the context of the Madelung equations, but it applies just the same to those more recent approaches. This, the Madelung equations are not equivalent to the Schrödinger equations unless a quantization condition is imposed. This condition is that the wave function is be single valued. Translated into the quantities of the Madelung equation, this means that this integral, essentially the line integral of the momentum, a loop integral of the momentum is quantized. 2 pi h bar times an integer for any closed loop. To the best of my knowledge, this condition has not yet found any convincing explanation outside the context of the Schrödinger equation. So let's just, to make it easier for us to talk about this, let's create some definitions, and let's call it the vorticity of our loop. Just that integer that determines what is the loop integral, and then the requirement that it be an integer, not just any odd value. Let's call that the Volstrom condition or the quantization condition. So how have people responded to this? Well, some haven't, right? That's always an option. You sort of feign ignorance. Another one, I think it's actually totally acceptable, is acknowledgement. You say, yes, it is an issue, but maybe the laws of nature just aren't pretty. You know, maybe there's this thing that seems very ad hoc, and as a term we've heard before in this context yesterday. Maybe that's just how nature is. Who says nature has to adhere to our, aesthetic, perceptions as physicists? And maybe it's just some effective theory, right? Maybe there's some underlying theory we don't know yet that ultimately will explain it. Right now, we're sort of at an observation stage. It's kind of like Kepler's laws, right? They provide a pattern of what nature looks like, but they don't explain it. It takes some deeper theory to actually get us there. And some will definitely say, well, it's just a calculation tool for me. And there's sort of lots going on in computational chemistry, for example, where you use this kind of approach with the density. And, who cares? It's just a matter of fact. And it's come some actual approaches. Again, in Smolin's work, essentially beables to describe momentum have a certain phase-like properties. Again, I don't have the time right now to go into any of the details. In my sort of work on this, I had essentially a sort of formal way to generalize the Lagrangian, where the most general time derivative you can add together with what's called an open endpoint variation. You can add a time derivative that is the derivative of something that's essentially has phase-like properties. Let's put it this way. Again, I'm not going to go into any of them right now. In 2011, Ilya Schmelzer proposed, working on this kind of thing too, proposed a certain regularity condition to address this. That creates its own issues in that it doesn't actually get you back quantum mechanics. It gets you back some other theory that may or may not approximate to quantum mechanics, because the vorticities are all one, and you need to have like multiple nodes. I'll come to that again in a second, but to sort of reconstruct what looks like a single node of the wave function in quantum mechanics. Then it's also mentioned what we heard about yesterday a little bit, the work by Manuel Lidarkhshani on the Zitterbewegung and stochastic mechanics, applying specifically to the issue within the Nelson formalism. And there's, for each of those, there's a lot to be said here, a lot that we could discuss. But the question I want to ask is, what if we don't impose it, right? Let's just say, okay, I like the CSD framework, this configuration space density type of approach. I don't like the wave function. For whatever reason, legitimate or personal, it doesn't matter. You don't like it. Well, can you make do without? Good question, but where do you start even asking this? So let's make some observation first about how differences to quantum mechanics might show up. And one thing you can ask, especially if you sort of approach this from a classical physics understanding point of view, you're saying, well, how can I have non-zero vorticity at all? And the reason you might ask this is because if you start with a configuration space and you say, I have a function that in the back of my mind is sort of a Hamilton principal function, a function from the configuration space to the real numbers. And then I say that my momentum, and essentially the velocity up to a factor, is the gradient of that function, then any loop is going to get you 0, right? The vorticity of any loop is going to be 0. So already, like, we have to modify this. S just can't quite work that way. But what you can then observe is that, well, what you can do is you can define this function S locally, meaning in some neighborhood. Pick a point, have a small neighborhood around it. As long as that neighborhood does not include a node, meaning an area where the density is 0, or where in quantum mechanic version, the wave function would be equal to 0. As long as there's no such point, you can define S. Problem is, if you have nodes, then you can't define the S globally as a single valued real function. Right? But locally you can. Let's make some more observations. The vorticity is invariant under changing the shape of your loop, under deformations of your loop, right? But only provided you don't move that loop through a node. And that's because from quantum mechanics, we know at nodes, the velocity field becomes undefined, right? The phase is undefined. In fact, it often is divergent. Not always, but in many cases it is. So the upshot is, before I got it, to wrap around a loop, right? To wrap a loop around a node, you need to have the right sort of dimensionality of node, namely n-2 dimensional, where n is your configuration space dimension. But lucky for us, those nodes are fairly generic because you need 2 conditions to define it. In, for example, quantum mechanics, the real and the imaginary part of psi each vanish, right? In the CSD type of model, you'd say that the density is 0, and also it is a minimum, right? Because density can't be negative. So the upshot is that any investigation to any broader physics that we might get by relaxing the quantization condition must focus on nodes. I think one more observation. In quantum mechanics or pilot wave theory, the vorticity is kinematically prohibited from changing, right? And that is because psi itself would have to change continuously according to the Schrödinger equation, right? It's a continuous evolution. But if the line integral can only take discrete values, there's never a way to sort of get continuously from one discrete value to another discrete value, right? You can't think, never mind what the laws of evolution are, you can't think of sort of wave functions that take you from one to the other. Right? So it's just not even possible to sort of talk about how that could happen. In the configuration space density frameworks, it is possible. Right? Kinematically, it would be allowed. Whether or not it does becomes a question, therefore, of the dynamics, of the laws of evolution. So a little bit of an aside. An approach we can take is other stationary states. And by state here, I mean not a quantum state, psi, but essentially a pair, rho and v, are defined on the configuration space that don't exist within the quantum mechanics of pilot wave theory. And the answer is yes. And essentially, the trick here to approach those is actually to go back to defining psi as a wave function, right, in terms of square root of rho and then v up to an arbitrary global phase, and you solve it, but you don't impose the single valued condition, right? You don't demand that single valuedness applies. So in this example you have in front of you here, we're looking at a 2D harmonic oscillator, and we plow through the normal sort of textbook math. I mean, most textbooks don't treat the oscillator in polar coordinates, but that doesn't matter. You can think of hydrogen atoms instead, or any other example that you find in your standard quantum mechanics textbook. You can apply, you sort of turn the handle and go through the algebra. You arrive at those 2 equations, and then the textbook is going to say, okay, in quantum mechanics, we demand m, the thing in the exponent here, be an integer that is required by single valuedness. And then the textbooks, they don't look back, they just keep going. It's an integer now. And then depending on the exact example you're looking at, this equation is going to be solved by some function. In this particular case, it would be the associated Laguerre functions. But whether it's your Bessel functions or your Legendre functions, it depends on the details. And for those, non-integer solutions generally exist. They're hard to find. Hard to find in the sense of hard to find in your reference math books. And we had a real struggle trying to just sort of, understand them better, just because any text you look at doesn't really deal with them very much. So we're still in the process of trying to understand them better. And the same logic, as I kind of indicated already, applies to other systems, right? So it is possible. It is an approach we could take. It is something to go down further. It is not what I'm going to focus on for the remaining minutes of this talk. What we're going to do is we're going to relax the quantization condition. We're going to do it numerically. We're going to add a little perturbation, right? And we add a little non-quantum perturbation. And by that, I mean a perturbation that changes the loop integral. So we're changing our initial conditions, right? And then we're going to track how this non-quantumness evolves over time. And in the back of our mind, if we say we really like those configuration space density frameworks, we might say, well, maybe is there any hope that that dynamically the non-quantumness gets sort of washed out, and what we observed as quantized nature we observed maybe is a dynamical result, and we don't have to worry about the Volstrom condition at all. Now, to take away the punchline, the answer is no, that doesn't seem to be the case, and you will have to worry about justifying the Volstrom condition. But it's a thought that you might have at this point. So we define this way of keeping track of the non-quantumness. It's a bit simplistic. There's a lot more to a non-quantum state and things we could look at. Let's just focus on that. Now, it's defined essentially as the value of the loop integral as a difference from the integer we get in quantum mechanics. Here, n. Now, n is ambiguous, right? But if we think of this as a small perturbation to an existing quantum state, then the quantum state defines n, and then nu, that parameter we're going to use to track the non-quantumness, is unambiguously defined. So what kind of perturbation should you add? Well, you can't just add any old perturbation. Like, you can't come up with any velocity field and just add it, because the velocity field still has to satisfy this condition that its momentum is the gradient of a function. Right? At least in any local, simply connected neighborhood that doesn't contain a node. You can think about, relaxing this condition. You can think about what happens if I don't demand this. It becomes sort of wild west of perturbations and initial conditions. Again, that it's a whole different topic, and is that justified, and so on. So there's a lot to be said here, right? But we're going to keep the focus on the case where that condition still holds. So what you can do, the simplest thing you can come up with, essentially you add a velocity field, like you see in the picture here, that sort of circles the node, right? And if you just, do a bit of trial and error with the math, you can find that this kind of field, where the loop integral is constant no matter how far out you go, no matter how you choose your loop around it, is essentially the gradient of a function that is just the arctan of essentially the angle, right? The angular variable. And then we can have this Nonzero parameter here that just tells us by how much is the initial non-quantumness. And this perturbation is generic, right? In the sense that if you want another velocity perturbation, you can just take this one and add to it something that is the gradient of a function, like a single, real valued function everywhere. And you can sort of create other velocity fields with the same initial vorticity. So what happens, right? And then this is where my student, Matt Scoggins, did a lot of great numerical work. But the answer is actually rather boring. Not much happens. So we looked at a whole bunch of examples, and it seems like the quantumness just sticks around. So let's look at to the oscillator, the same example we just looked at in the context of the non-quantum stationary states. Right, so let's take an oscillator, and we took a state. In this case, what you see is the 3,0 plus I01. Just an example. We explored a lot of different ones. But the non-quantumness, what you see on this graph here, is just dead flat. It just does not go away. It just sticks around. And as I said, you get the same thing with other states, with other initial values, with other systems, not just the harmonic oscillator. So maybe we just went a bit, maybe it's all a bit too boring, right? I mean, you can argue maybe there's something about momentum, angular momentum conservation here, and so on that stops anything from happening. We have to be careful what kind of concepts we borrow from quantum mechanics, because we're not doing quantum mechanics. So we shouldn't assume that results from quantum mechanics just carry over. We have to be very careful about that. But right now we're sort of exploring this numerically. So let's mix it up a bit. So what we decided to do is let's add some interaction potential. And so we started with the Gaussian, we tried other shapes too, essentially a time-dependent potential that abstractly might represent some kind of interaction. Right? And there are lots of different choices here. Is that going to change anything? And it appears that the answer is no. We get exactly the same graph. The non-quantum, it doesn't grow, it doesn't shrink, it simply sticks around. So this vorticity is essentially conserved. And we then were like, hey, we need to explore this more deeply. We've mixed up the initial states with perturbations in the density just to get away from any well-defined finite sum of eigenstates of the oscillator, for example. Right? So we added an arbitrary, so randomized density perturbation. And same thing. Right, so really that there's a conservation law here that it looks somewhat like angular momentum conservation that applies in the non-quantum case around the nodes, and so we conjecture, right, therefore that it's dynamically maintained even if it's not kinematically constrained. Never mind whether it is an integer or not an integer. And if your hope had been the one that I mentioned, that maybe we don't have to worry about the Volstrom objection because it gets dynamically, it disappears asymptotically or something like that over time, well, you're disappointed, right? That doesn't happen at all. The dynamical evolution does not reduce or remove the non-quantumness. So if you propose one of those frameworks where you don't have a wave function and you deal with densities, whether they're a many universe type of model or whether they're real ensembles, you'll have to address this. And then, so where do we take this from here? And this is an ongoing project. So there's a lot, I think, to be learned here from fluid dynamics about how nodes behave, or how this vorticity around nodes behave. Right? And that's something we're doing right now. There's a lot of systematic work we could do. We are doing on recovering results from quantum mechanics without assuming quantum mechanics, right? It seems so tempting to jump back to psi because we know all those results. It's linear, it's beautiful, right? But we have to not do that because we don't want to subtly assume certain global properties of psi. And there's a lot more we could be doing: measurement theory, explore actually what the non-quantum evolution looks like, never mind the degree of quantumness, right? So what kind of trajectories do we get? Field theory, sure. I mean, there's always more you could do, right? But I think the upshot that I want to end on is that right now, the Volstrom objection, it's there and you have to deal with it if you want one of those models. It cannot be, at least the indication is that it cannot be dynamically explained. Thank you very much.